Right, the recording has started, and we'll share the charts. So can you see the charts and can you hear me all right?
Yep.
Yes.
Okay. Okay, well, good morning, everyone. Thank you for attending what I'm calling this Swan Song workshop, the last one that I am planning to give before my retirement date of next Friday. Oh, we have a couple more. Yeah. So and I'd had a few people request this topic, and I thought it only made sense that after telling you all the ways in which things can go wrong, that I should tell you how to make it right, how to do things properly. I've done some of that along the way, but I think it was just good to pull it together and here are the strategies, tried and true techniques for getting things right from an EMI standpoint. So mitigation strategies. So if you remember nothing else that I ever told you, do you know where your currents are flowing? So, okay, that's a question rather than a statement, but that's the basic message is know where your currents are flowing. It's an EMI mantra, follow the current. So here's all the stuff I'm going to be talking about, and let's just get on with it. So we're going to start with a review of the basic physics, because to my mind, you need to understand the physics and the mechanisms you're dealing with to understand how to mitigate them properly. So I'm going to go through some theory, minimize the math. I'm going to show some math and equations just as review, but I won't rederive anything, I promise. But we'll get into the practical applications of all this. So first thing is just Gauss's law, and the basic premise there is that a charge produces an electric field, right? And where you have an electric field, if you integrate it over some distance, you will get potential. That's the very definition of potential, is the electric field integrated over distance. This electric field is defined in units of volts per meter. So you integrate a 1 volt per meter field over a meter, you will have a volt across that meter of separation. When you apply a potential between a pair of conductors, you will deposit charge on them, and capacitance is defined as charge divided by potential. Friend and colleague in the EMC Society, Bruce Archambault, who was actually the general chair of this year's EMC symposium in Raleigh that I'll be attending as a civilian or a private citizen. And I'll probably have a sign saying we'll work for food, but that's another story. Bruce Archambault describes a capacitor as a bucket of electrons, or a bucket of charge, right? But the bigger the bucket, the more charge you can hold for a given potential, right? So, but anyway, capacitance is defined as charge divided by potential. And so if our potential is time varying, well, then ipso facto, our charge must be time varying. And what's time varying charge? Class? Current. The time varying charge is the very definition of current. And if it's current flowing through capacitance, that's called displacement current. So it's another one of these things that I don't know if they're still teaching it this way, but when I was an undergraduate, umpty years ago, they first teach you that current doesn't flow through a capacitor. And I really wish they would stop teaching people that, because it's wrong. It's like, it's true from a DC standpoint, but then you start increasing the frequency. Yes, you get displacement current. I don't think it helps when you teach young people that current doesn't flow through a capacitor except when it does. So anyway, you get displacement current through capacitance. Now I'm showing this, showing the familiar capacitor symbol, but the whole idea here is that you will have capacitance between any pair of conductors, anywhere, whether it appears on your schematic or not. So you need to think in terms of capacitance that is going to be present between any pair of conductors anywhere. It's just a matter of degree. And at what point does it start to allow displacement current to flow that might compromise your circuit's behavior? So, so another part of this is if you just look at the definition of capacitive reactance, or how we arrive at that, expressing things in the frequency domain here, we have the familiar expression for capacitive reactance of 1 over j omega c, or 1 over j2 pi fc. So the implication there is that that reactance, or the impedance presented by that capacitance, decreases with frequency. So that means you can get more displacement current as frequency goes up. It's a more pronounced effect. And thinking in terms of unintentional capacitance, it means you can get more capacitive coupling with frequency, which we'll get to here presently. So now changing our focus to magnetic concerns. So Ampere's law tells us that a current produces a magnetic field or flux. And we think in terms of both the H vector, the magnetic field intensity, and B, the magnetic flux density. And the right-hand rule, not really going to spend a whole lot of time on this today, because mostly we're dealing with magnitudes. But if you're in the middle of troubleshooting a problem or what have you, it's a good idea to understand what direction is the flux going and what is the polarity or coupled flux and all that good stuff, coupled potential. But you point your thumb of your right hand in the direction of current flow, and the fingers will wrap in the direction of the magnetic field or flux. And the other side of magnetic picture is Faraday's law, which says that magnetic flux, a time-changing, time-varying magnetic flux through a loop, will induce a potential or electromotive force, or EMF, in that loop. Those three terms are all pretty much interchangeable: EMF, electromotive force, potential. And so that VEMF equals minus dphi dt is the simplified expression of these. This is one of Maxwell's equations, right? Oops, sorry. It's something I didn't mean to hit there. Okay, everybody still seeing the presentation? Is anybody still there?
Still here, negative on the presentation.
Oh,
We're seeing the
so
people that are visiting.
did you see any of it?
Yes.
Okay, so it must have just gone away. All right, the mouse went somewhere I didn't mean for it to go, and it must have gotten out of that mode. Okay, is it back?
Oh, we're seeing the attendees.
Must have stopped sharing for some reason. Okay,
There you
back.
go.
All right. All right, so did you see the beginning of this slide?
Yes.
Okay,
Yep.
so I don't need to go back. All right, thank you. Sorry about that. Yeah, the mouse just kind of went somewhere and disabled the sharing, and I didn't mean to do that. So, okay, let's try that. Let's do this again. So a time-varying magnetic flux will induce a potential or EMF or electromotive force in that loop. And all I will say about the negative sign, it's also the right-hand rule is when the magnetic flux is going through a loop, as shown here, pointing downward, the polarity or the direction of the electric field and the potential will be such that it counteracts or impedes the direction of the incident flux. Okay, so the flux is pointing downward. You want well, you don't want, it's just physics. It's what Mother Nature says is going to happen. The induced potential is going to be in a direction. When you wrap your fingers around the loop in the direction of the induced potential, then your thumb will point in the direction of the opposing flux, which will be upward. So you see that it seems like I don't have my mouse now, but there we go. All right, so I've shown the arrows here showing the polarity of the induced potential wrapping around in a counterclockwise direction. So if you wrap your fingers of your right hand in that direction, your thumb will point upward. So that in the direction of the flux that will oppose the incident flux. Okay, anyway. So it is a function of loop area. That'll be a recurring theme here. So just a tiny bit more theory. Well, maybe a little more than a tiny bit, but a bit more theory before we get into what we do about all these things. So recall our electric Hertzian dipole. It's our elemental electric dipole, or it's called a Hertzian dipole, and it will have radial and angular electric field components, as well as this H phi, that wraps around in this direction. And then our electric field lines, if you look in a cross section, will look more or less like this. I'm not going to say a whole lot about this. I'm just showing this for context when we get to the magnetic or loop dipole. But excuse me, as I talked about in the dipole session, when you try to do a near field analysis, particularly of the electric field, it's non-trivial. I would even say it's fraught with peril. It's got a very huge error bar associated with it. But when you look at the magnetic field around a long current carrying conductor, it could even be a displacement current, right? But usually we talk about a current carrying wire for this application. The magnetic field is given by this I over 2 pi r. This is very accurate, and current probes employ this very principle. When you clamp a current probe around a cable or a wire, you're not measuring the current directly. You're actually capturing the magnetic field lines, magnetic flux, and converting that into a potential. And then your calibration curve gets you back to the current that had to have induced that magnetic field and so forth. But this gives you a very accurate description of the magnetic field around a long current carrying wire. And this is handy for inductive crosstalk analysis, and we're going to get into that here presently. So, as promised, we look at the elemental magnetic dipole. I didn't really spend a whole lot of time on this in the dipole session, but I wanted to hit this because some of this is a bit key for understanding twisted pairs and some of the stuff we're going to talk about here. But if you look at your elemental dipole, it's the magnetic dipole, it's a loop as opposed to just a very short straight current carrying element like the electric dipole. So this is a loop with radius b, and the magnetic field lines look very similar to the electric field lines from the previous plot. So you're looking at a cross section here, basically like head on to the loop here. So here the current's coming out. I forget, is the dot going into the page or out? I forget.
Dot's coming out.
Dot comes out and the X is going in. So yeah, the current's flowing in that loop, and then your magnetic field lines look like this. We tend to think, we have to emphasize the far field because the math and the analysis gets easier. But I would just want to, the vector magnetic moment is a function of the loop area. It's the current in the loop multiplied by the loop area. So if it's a circular loop, it's just pi times the square of the radius. But we tend to think in terms of the far field because it's just easier to think about. The analysis is much simpler. And so that h sub theta component is what dominates in the far field. It's normal to the plane of the loop, and it's nice and straightforward. That's all you have to think about in the far field. And that's what we emphasized in the dipole section. But if you look right near the loop, it's that radial component can be very strong in the near field, and it will dominate when you're right near the loop. And that, just parenthetically, is the raison d'etre of RS 101, or radiated susceptibility for magnetic fields test. You're putting a current through this coil, and you're providing a radial component, that h sub r, to impinge upon your test article. So this is actually pretty central to discussing twisted pairs, which we'll get to. So fear not, we'll come back to this. And then just the elemental dipole, of course, is basically looking at the limit of as b approaches 0. But for any practical sized loop, this is probably probably an example that's in any electromagnetics textbook you may have used. But this gives you that radial component of the H vector along the axis, going through the center of your circular loop. So I just kept this in here for reference, but this just says that right near a loop, you will have a very strong component, a radial component of the magnetic field along the axis. And that's really what twisted pairs are addressing. So we'll get back to that here presently. So the bottom line with these, with Hertzian, with our elemental dipoles, is whether it's a Hertzian dipole or a magnetic dipole, it comes back to current. Currents produce radiated fields. So basic message there is control the current, control the fields. Almost like I've said that 100,000 times, right? And 100,001, right? Remember nothing else. Do you know where your currents are flowing? Almost like I put that chart in there on purpose. My spidey sense tells me you're going to see it a few more times before the end of the presentation. Okay, everybody with me so far? Can you still hear me?
Yep.
Okay,
Yep.
haven't dropped sharing again. Okay. All right, so just a review. Is there a question? Okay. All right, so just a review of some basic terminology. That EMI, electromagnetic interference, as the name implies, is all about. It's the phenomenon in which one component subsystem interferes with the proper operation of another subsystem due to the propagation of electromagnetic energy. And electromagnetic compatibility is the discipline of trying to prevent that, ensuring that the components don't interfere with each other. Okay, so we sometimes, myself included, guilty as charged, we can lazily and sloppily use these terms interchangeably, but they are different, right? EMC is all about preventing EMI. So, and then other basic terminology is just, we have our culprit or aggressor, which is a component or subsystem that is an emitter of electromagnetic energy or unbridled evil, as this example shows. Then a victim. Yeah, I know I need to update my cultural references here, but this is what we got. But our victim is a component or subsystem that is susceptible to electromagnetic energy, and your coupling mechanism is the process by which this energy couples from a culprit to a victim. So to have an EMI problem, you need all three of these. You need a culprit, a victim, and a coupling mechanism. And to fix it, you need to address at least one of them. So you need to reduce your culprit emissions. That's ideal, right? If you can just keep your culprits from being noisy, then you don't have any problems. That's not always practical, but that's ideal. Or you reduce the susceptibility of your victims, you just make them more robust, or you reduce the coupling efficiency. So you got to do at least one of these. And with the stuff that we're going to be talking about, if there's some gray areas, are you really reducing emissions or are you reducing coupling efficiency? But we'll get into that here presently. That's the main point of the talk. So let's just talk about some coupling mechanisms. We need to understand what these coupling mechanisms are to mitigate them. So we have conducted, radiated, and then crosstalk, capacitive, and inductive. Crosstalk is sort of a subset of radiated. It's you can kind of simplistically think of it as near field radiated coupling, at least to my way of thinking. That might spark debate amongst a lot of purists, but those are the three basic types of coupling mechanisms we're dealing with. So conductive coupling is at least what I would consider to be synonymous with common impedance coupling or ground balance. It's when you're actually literally sharing conductive paths. So like when I first started as an electrical engineer umpty years ago, we never thought about current. We were just passing signals from one circuit to another and tying both of our circuits to what we called ground, which is an EMI 4-letter word. Pick which letter you want to Well, there's 6 letters, isn't it? So you got to admit 2 letters, I guess, to make it a 4-letter word. But you know what I mean, right? We connected them to a common reference, and we didn't even really think about where the current was flowing. And when you're running things at a couple kilohertz, you can get away with that, right? But so all there, when you are dropping a potential across an impedance, some current will flow, and it's got to get back to the source. Kirchhoff says so, or Mother Nature says so, and Kirchhoff was the reporter. So that current has to come back to the source, and all the currents from these signals are going to come back on a shared path. So that can create a potential difference between these 2 circuit references. And if that potential difference is significant enough, it can compromise the performance of your receive circuit. Right? If it lifts the ground reference here with respect to the signals that you're transmitting, you can get signal errors. And if it's a digital system, it can cause bit flips, which can cause your system to not work anymore. So simple way to address that issue is you provide separate and dedicated return current paths for each circuit, and basically treat each interface as a differential interface. We'll get more into that. But if you just provide a dedicated current return path for each circuit, then that significantly mitigates common impedance or conducted coupling. So for radiated coupling, kind of as the name implies, well, so time varying potentials and currents in your culprit circuitry will produce radiated emissions. You know, stuff that we've talked about in the dipole sessions and other sessions, and just our elemental dipoles we just talked about. If you have time varying currents and potentials, they will generate radiated fields. And then when they impinge upon a victim circuit, they will induce potentials and currents in that victim circuitry that then can couple into sensitive equipment inside here and disrupt its operations. So electric field, or is synonymous with capacitive crosstalk. Basically, you have a culprit conductor and a victim conductor, and again, any 2 conductors anywhere in space will have capacitance between them. You have no choice in the matter. Mother Nature says so. It's just a matter of degree. And that capacitance will allow a displacement current, a noise current, to flow between the conductors. And now you have an impedance divider. So the coupled potential in your victim circuit is going to be the result of that impedance divider. So whatever your culprit potential is here, you know, that's going to drop, that noise current is going to flow through the circuit. The capacitance will complete the circuit, and the coupled potential, the victim potential, is just going to be the result of that impedance divider. And the coupled potential, note again here that this impedance here decreases with frequency. The capacitive reactance decreases with frequency. So that means that the noise current and the coupled potential will increase with frequency. So all this fits into how and why we EMC engineers keep harping on frequency. That all of these effects, by and large, get more pronounced with frequency. So when we look at magnetic crosstalk, you have a culprit and a victim. You have some current flowing in your culprit that generates a magnetic flux that can then couple through your victim loop, and it couples to the loop, not to the conductor itself. That's a key distinction between capacitive and magnetic, or capacitive and inductive coupling. Capacitive coupling, the coupling is directly to the conductor. With magnetic coupling, inductive coupling, it's to the loop formed by the victim and its reference. So, and again, just understanding the physics and the mechanism is key for understanding how you mitigate problem. But so when you have this flux coupling into the victim loop, a time varying flux will create a potential, will induce a potential in that loop. And again, as we talked about before, the induced potential will impede or oppose the incident flux. So in this case, if the flux is going into the page, the induced potential will be in a counterclockwise direction, so that so to counteract or oppose the incident flux, and that's Lenz's law. And here again, the coupled potential will increase with frequency. So both of these effects will get worse with frequency. So one of the basic things you can do to minimize radiated coupling and crosstalk is just physically separate your noisy and sensitive circuits, right? That just the coupling will drop off with distance. So that's just one of the most basic things you can do is just keep your noisy stuff and your sensitive stuff separated. And it may not get rid of all your problems, but it's certainly it's certainly a big step in the right direction. So now we'll talk about shielding, okay? Particularly with respect to electric fields and capacitive coupling. So this is just going back to our capacitive coupling model where you have your impedance divider. So this shielding basically, all these shielding concepts work with respect to both capacitive coupling and what we would call traditional radiated emissions in terms of electric field anyway. So when you put a shield around your culprit, well, what is that doing? Well, what you want is for that noise current, you're providing a path for that noise current to divert it away from your victim. It's not making the noise current go away. It's just providing an alternate path. But a path to where? Where do you want that current to go? Any volunteers? What does Kirchhoff say? Or what does Mother Nature say that Kirchhoff reported?
Back to the source.
Thank you. Who said that? Who gets the gold star?
No,
Hi, Noel. How long have you been retired, Noel? Need to give the younger folks a chance.
that's a long story. Go ahead.
Anyway, but you get a gold star anyway. All right. Yes, it goes back to the source. That's our mantra. So in order for that to be done properly, you need to provide the path. Right? It's going to get back there eventually. It has to. Mother Nature says so. But if you don't provide the path, it's going to follow some less efficient path that probably will generate more emissions and couple into circuitry you'd rather it not go. So you need to provide the path all the way back to the source. A good low impedance path. All right. So low impedance bonds all the way back to the source. And the shield is only as effective as its termination. I really should say terminations. So you want a low impedance termination of the shield to the back shell and the connector. 360-degree coverage is ideal. And a low impedance connection, low impedance connection between your mating connectors, right? That's another weak point. I mean, the metal housings of your connectors may not make great contact. That can compromise that connection. You want a low impedance connection between the connector and the chassis it's mounted to. And you want a low impedance connection between the signal reference and the chassis, right? So, sometimes a lot of people think they want to separate their signal references from chassis, and that can compromise this ability for your noise currents to get back to the source. And if you have a really strong reason to separate a signal return from chassis, you may need to consider at least putting some capacitance here so that those AC noise currents still have a path to get back to the source. I'm never a big fan. I'm never a fan at all of lifting signal references from chassis because it invites these kinds of problems. You need to have a damn good reason to do it, and you need to really know what you're doing to do it properly. So now noise currents may well exist in your load circuit as well. So it's the same deal. You want to make sure those noise currents that couple to your shield have a good low impedance path all the way back to their respective sources. So terminate the shield at both ends. You want to provide low impedance paths for noise currents to return to their respective sources. If you think that lifting the shield at one end is a good idea to avoid a ground loop or single point ground, what have you, you're rather missing the point. The shield should not be part of your of your signal reference path. The shield is a shield, and you want to provide a path for those noise currents to get back to their sources, and a proper termination on both sides of the shield is how you do that. Okay. So now we look at shielding the victim. Excuse me, I need to take a sip of coffee. I call them my performance enhancing drugs.
Would you consider an unterminated shield an antenna?
Yeah, that's exactly
you.
what it is. In fact, I don't actually really say much about that, but when we get to the end for open discussion, we can talk about that. And regarding my performance enhancing drugs comment, it's more functionality facilitating drugs. Anyway, moving right along. So to shield the victim, what happens when you shield the victim? It's really the same general concept. You want to shunt that noise current away from your signal conductor. But there again, where does it ultimately need to go? Well, we already know that, right? It needs to get back to the source. So, so you need to provide the path. You know, if you just terminate it to the chassis of your victim circuit that's different from your culprit circuit, that's only part of it. That's great. That's a necessary thing, but it's not sufficient. So you want to bond that chassis to structure. And okay, if you don't have a metallic structure, then you gotta think that through. But by and large, we're dealing with metallic structures. But this is a big part of why we do that, why that's a good idea. You bond the chassis to structure so that then that noise current has a path to structure, but okay, it only gets so far on structure. The culprit equipment needs that chassis also needs to be bonded to structure, and that signal reference needs to be tied to chassis. So you need to consider that entire path for those noise currents to get back to the source. Because if you don't do that, those noise currents are going to flow. The technical term is, I believe, ever which a ways, and that is how noise currents get where you don't want them to go. If you don't provide that controlled low impedance path, they will get into circuitry that you don't want them to get into. So provide low impedance connections all the way back to the source, and the shield is only as effective as its termination, and indeed the entire path back to the source. So revisiting this from the grounding and shielding session, a pigtail termination has significant inductance. You're basically putting an inductor in line with the connection. That's exactly what it is. So when you put an inductor there at higher frequencies, that will allow some potential difference to form between the shield and the chassis. And that will allow some current to flow, some common mode current to flow across that connection impedance. And that will, in turn, induce radiated fields. And to Mike's point, this gets much worse if this is an open circuited, if the other end of this shield is just floating like this. The implication here, maybe I should have put a ... here, is the implication is that this is actually connected to something on the other side. But if the shield is open circuited, then it's much worse, and then it will behave as an antenna. And so these radiated fields will be even worse, but it's the same general concept. And so a poor termination on the victim shield just will allow noise currents to flow into the victim circuitry. It will allow potential difference to form between the shield and chassis, allow this current to flow. And with that potential difference, now you've got the capacitance between the shield and the current carrying conductors that will allow this noise current to flow into the circuitry inside the box, and then put some noise potential across your victim circuitry. And that's precisely what you don't want. So when you put a pigtail in there as your shield termination, you are compromising its effectiveness, and that will get worse with frequency. So a proper shield termination with 360-degree coverage, it will minimize the inductance of the connection. It will minimize those potentials and currents in the culprit circuitry and reduce emissions. And it will also reduce the coupled potentials and currents in your victim circuitry. So it's all the stuff that you want. And here's
Given the choice of pigtail or open, say due to thermal conduction concerns, is there a preference?
Oh,
Or is it something you test out in the EMI chamber?
the evil of two lessers.
Yeah.
Well, a question often comes up about like inner shields. Like if you have a bunch of twisted pairs with individual inner shields, and then an overall shield. The overall shield, actually, that's basically what this picture is addressing. This is, I believe this is verbiage I specifically wrote up to be and requested to be included in this NASA standard document. But terminating an overall shield with 360-degree coverage is, I mean, it's stuff that's, we know how to do that, right? That's pretty standard. But doing it with a bunch of individual shields is a little harder to do, right? To like maintain 360-degree coverage all the way up to the connector, especially when it's inside a larger bundle. So we have, I think part of the verbiage I wrote up was that the important thing is maintain the 360-degree coverage on the overall bundle. If you have inner shields and it's, you know, if it's not feasible to maintain that 360-degree coverage, there are ways to do that, like with a braid sock or what have you. But it's, I think they're non-standard techniques or what have you. But if a pigtail is absolutely necessary, the guidance is keep it absolutely as short as possible. Because it's not that it's completely ineffective. It works just fine at low frequencies. It's just the inductance of it is going to provide a higher impedance as the frequency goes up, and to the point where it, at high enough frequencies, it's basically going to be essentially an open circuit. So if it is a choice between a pigtail and a fully open, I mean, you want to provide some termination there. It's just, you know, if it's got to be with a wire, make sure it's absolutely as short as possible. And it's really, and I think the verbiage I wrote up is that it's really only acceptable to use to do that when there's an overall bundle shield that's really providing your overall protection from the outside environment. Yeah, does that help?
Yes.
Okay. Okay, so this is just you know, pretty much standard practice for overall bundle shields. We know how to do this. You know, do we do it all the time? That's a question for discussion, but this is at least the ideal. So, all right. So summary of RF shielding. It's RF shielding is effective for minimizing. Is waiting in the lobby. Can anybody let Nelson in? I think I keep trying to let him in, and he's not able to get in. So sorry about this.
Just click out of the bottom there. You want to go to focus on the PowerPoint window. So
I'm sorry.
beneath that Teams window,
Yeah.
just no, underneath the whole window. Yeah, just click that thing.
Okay. All right. Is everyone still seeing the charts?
Yeah.
Okay.
Now.
But they went away.
Yeah, we were seeing.
All right. Sorry about this. This
All
is
Still sharing.
all right. It says still sharing on my screen. Let me just stop sharing and I'll come back.
No, it's fine.
Oh, it's there? Okay. All right, good. All right. So RF shielding is effective for minimizing radiated electric field and capacitive coupling. The shield does not make noise currents go away. It simply redirects them away from sensitive circuitry. To be effective, they must provide a low impedance path all the way back to their respective sources. So that the shield is only effective as its terminations. No pigtails. And you didn't hear that little caveat that we just discussed. So 360-degree coverage is ideal to minimize inductance. And I've shown this before, haven't I? You know where your currents are flowing.
What?
All right. This annoying window keeps blocking things. Let's put this down here. Okay, all right. All right, so now we're going, well, anybody have any questions about shielding? Because we're gonna shift focus here to magnetic and inductive crosstalk. Okay, so just review of our inductive crosstalk model. You have current in your culprit conductor, generates flux through your victim loop, not directly to your victim conductor. And then that induces a potential in your victim loop. Okay, so if we look at our culprit current, you know, it generates this magnetic flux. And remember, remember Kirchhoff, it's never just a current flowing in one direction. It's got to have some return path back to the source. Okay, so we want to provide a return current path near the send path. All right, one of the biggest issues with magnetic coupling is if you do just treat your send path as just some conductor going off to a load somewhere, and then the return path is whatever it is, like on structure or what have you, then you can have a huge loop there, and that will generate some significant magnetic emissions. So one of the best things you can do is just provide a return current path that's as close as possible to the send path. Okay, so the current in the opposite direction will produce a field that mostly offsets the field from the send path. And if you go far enough away from that pair, then they basically will cancel. But right in the vicinity of that pair of wires, the fields won't completely cancel. The non-zero loop area, if we go back to our little loop model, you know, right in the vicinity of the loop, there will be this significant radial component of your magnetic field coming off normal to the plane of the loop. So a non-zero loop area means there will be non-zero emissions. So what's an additional step that we can take here? And don't anybody look at the subject line for a hint. That's exactly correct.
Twist
Whoever didn't
them.
say it out loud. Twist the pairs, twist the send and return conductors together. Yeah, if I give this presentation again, I'll remove the hint from the subject line, but there we are. Oh, it's to be consistent with my list of topics because it says twisted pairs. So anyway, so yeah, you twist the send and return conductors together, and so what that does is that you can model it as a series of loops with the currents in adjacent loops flowing in opposite directions. Now, obviously, what's really happening is that the plane of the loop of each loop is continuously moving, right? So the direction of the normal component of the magnetic field is constantly turning. But a simplistic way of looking at it is if it really is just a sequence of loops that are in opposite directions, right? So the emitted fields from the adjacent loops will mostly cancel. Right, so you have this pair of loops, those fields will cancel, this pair of loops they'll cancel. So the worst case emissions are going to come from the loop area of a single half twist. Okay, so even if you have an odd number of twists, and I did essentially deliberate. I could say, oh, I deliberately did this, but it was a happy accident. I did only 5 loops here and realized, oh, okay, I can illustrate this point where, you know, if you have an odd number of twists, then okay, you're not going to get full cancellation. But if the net field is from a single half twist, that's a much lower loop area than if you didn't twist the conductors at all. But that's precisely why you twist. The first thing is just reduce the loop area. That helps quite a bit. And then when you twist them, that gives you additional cancellation and reduces the net emitted field to something much smaller than you would have otherwise. Right. So then from a susceptibility standpoint, this is actually, I think, a little bit easier to understand, right? So you have your incident flux that couples to a victim circuit. And again, it's a loop. It's the loop formed by the victim conductor with its return path. So again, capacitive coupling couples to the conductor directly. Magnetic flux is coupling to the loop formed by the victim conductor and its return path. So here again, if you, and well, the total flux is the integral of the B vector over that entire surface area of the loop, which then induces this potential in the victim circuit. But again, it's a function of loop area. So we reduce the loop area. So here again, if we provide a return current path immediately adjacent to the send path, we reduce the loop area and reduce the available loop area through which any flux can couple. So that helps right there. But here again, we take that additional step of twisting the send and return conductors so that now that plane of the loop is continuously rotating. But if we take the simplified model of just thinking of it as a series of loops that have opposite polarities or opposite directions, then the induced potentials in each adjacent loop is going to be of opposite polarity, right? So if you think of the flux coupling into the page, then the induced potential on this first loop with blue as the positive conductor, then the induced potential is going to be in the counterclockwise direction, so that the resulting, it's in the counterclockwise direction so that it opposes the flux going into the page. Likewise, when the flux is going into the page for this loop, then did I draw this correctly? Okay, yeah, the flux is always going to be in the counterclockwise direction to counteract the potential is going to be in the counterclockwise direction to counteract the flux going into the page. So with the send and return conductors reversed now, the induced potential is still in the opposite, it is still in the counterclockwise direction, but it's in the opposite polarity to what you have in this loop, and so on. So these two polarities will cancel. These two induced potentials will cancel. These two will cancel. So here again, the worst case net coupling comes from the loop area of a single half twist, which is going to be a much smaller loop area than if you did nothing. So just getting the return path to be immediately next to the send path, that reduces the loop area. That does a lot right there. And then when you twist the conductors, it gives you that additional mitigation such that the coupled potential in these adjacent loops cancels. So that's the physics of why we twist the pairs. So minimizes the loop area, and it helps with both emissions and susceptibility. And then when you twist them, it reduces the emissions and susceptibility to the equivalent loop area of a single half twist. So this is, of course, something we do with cabling, with wires. If it's not practical, say on a PC board, just minimizing the loop area alone provides significant benefit, just providing that return path as close as possible to the send path. I think I have heard of some of people doing kind of virtual twisting, like running a short segment of a conductor and then go through a via and then go to another layer.
Like with a board with like 15 layers or something like that.
Something like that.
Yeah.
I don't know that I've ever actually looked at a board layout that does that, but I think I've at least heard anecdotally of people doing that. Now it may be, I mean, your mileage may vary. The designer has to, make the appropriate decisions there, but it may well be that when you're dealing with, if you're able to get the return path very close to the send path, and if the traces are not very long, that may well be enough, right? Obviously, trying to do a virtual twist on a PC board is a bit non-trivial, and it's probably going to drive up your production costs and all that sort of thing. So only do that if it's absolutely necessary. But twisting wires is something we do all the time, and it's a straightforward thing to do. And I mean, I've certainly done it, but I mean, you can just buy twisted pair. You can buy shielded twisted pair. We'll get to that too. So, have I mentioned that? Do you know where your parents are flying? All right, balanced differential interfaces. We're shifting gears here. So does anybody have any questions or comments while before we shift to another topic? Okay, so this actually is kind of a piece with everything we talked about. All of it kind of blends together. But something that works very well is you provide balanced differential interfaces. So instead of just a signal, some potential or current with respect to a reference, you actually provide, you have your positive potential, like half of the desired potential, right, of your signal. You provide half of it in the positive direction and half in the negative direction. Right. And and if everything is balanced, if the potentials are balanced and the impedances are balanced and the currents are balanced, well, from an emission standpoint, if everything, if you have equal and opposite potentials and currents, then the emitted fields cancel theoretically. Right. That's what you want. If everything is equal and opposite and well balanced, then you should theoretically have zero emitted fields or practically very low emitted. From a susceptibility standpoint, then any incident field, whether I'm showing capacitive coupling here as an example, but whether it's capacitive or magnetic coupling, in principle, you should get the same amount of energy will couple to both conductors. And I mean, if you think of capacitive coupling, as an example, right, that it's all an impedance divider, right? So with a balanced impedance to the reference, then it's going to be the same potential or the same current and same potential will couple to each conductor, right? So it'll be a common potential on each of the positive and negative sides. And if it's a true differencing amplifier receiver configuration, then it's going to subtract out that common mode voltage and just give you the difference, which is exactly what you want. And these types of circuits, by design, have excellent common mode rejection. That's exactly, when you see common mode rejection ratio, that's exactly what that means. You have some common mode potential, the same potential that's coupled to both conductors. It's got 80 dB of common mode rejection ratio, then it's going to knock the resulting signal that you will see on your differential received signal is going to be 80 dB down from that common mode potential. It's been a little while since I've looked at specs, but 80 dB is a pretty good number for common mode rejection. We use these kinds of interfaces all the time. Some of these go back many decades. 1553 and RS422. Let's go back 50 years. Certainly 30 or 40. I mean, they were in common use when I
More
started.
than 50.
Yeah, 1553 is definitely more than 50 years old. LVDS is a bit more recent, but it's becoming standard. Now it's differential-ish, or it is a differential interface. It's not completely balanced. So I keep it in here because differential interface that we use all the time, but there's a little caveat that it's not really a fully balanced. The impedances aren't fully balanced, as we've learned, but it still works pretty darn well. And then for analog circuits, when I was still cutting my teeth as an analog designer, when I was introduced to the differential or the instrumentation amplifier configuration, this was a game changer. Like this pretty much eliminated common mode coupling. So if you've never used an instrumentation amplifier in an analog system, you should. These are really the way to go. I think most designs that I've looked at, I mean, I haven't done analog design in more than 20 years, but designs that I've looked at for like, low level temperature sensors or any kind of transducer or something like that, if it's done by an experienced analog designer, I see this kind of configuration all over the place. So these instruments, the idea is that it presents a good high impedance to both the positive and negative lines, and it's a common impedance, right? It should look the same, and so it just sees this high impedance of each of these op amps, or however they're implemented physically, and then it just differences the two, and it knocks out the common mode pretty much to zero, or something ridiculously low. So anyway, if you haven't used the instrumentation amplifier, and this may well be what's inside some of these configurations, I don't really know, but remember, the world is analog. Digital is just an approximation. So the digital interfaces may well use something like this. So another technique is what we call the method of images. So if you just have a conductor in space with no ground plane, with some potential and current on it, well, the fields radiate. And that's just physics, right? You have some current, it's going to generate some current potential, it will generate fields. But if you put it over a ground plane, that implements the method of images. The fields line up such that, I mean, it's just theoretically with an infinite ground plane, right? Okay, there's no such thing. I've never seen one. If you have, I'd love to hear about it before I retire next week. But but practically, it's just sufficiently large to behave as an infinite ground plane. The fields will line up as they would if there were actually an image conductor or image wire or cable underneath the ground plane with the opposite potential and opposite current flowing on it. Okay. Now, physically, what's happening is that you're providing a capacitive coupling path for that current to return on the ground plane, right? But in terms of understanding what the fields look like, that's where the method of images comes in handy. Is that the fields will look the way they do if there is actually an image conductor underneath the ground plane, like looking in a mirror, kind of literally, right? So that's pretty much what I just said. So the real point here is that while a fully enclosed Faraday cage is ideal, like full shielding from a Faraday cage is great, but just because you may not be able to achieve a fully enclosed Faraday cage doesn't mean that you still get some benefit by simply routing your conductors near a ground plane. Okay. I hear that sort of thing. Oh, well, we can't establish a Faraday cage, so all is lost and it's useless and we shouldn't do anything because, blah, blah, blah. Like, no, that's you still get significant benefit just putting your conductors over a ground plane. So there again, when you hear us say, put stuff over a ground plane, this is why. It's not just like whatever. It's not just something we're saying to because we like the way the words sound. Although I guess maybe that's part of it. Anyway, okay, so now we're gonna put all this together. I was having trouble coming up with any metaphor to describe this next part here. So if any of you have any suggestions, please let me know. But now, I will say when I showed this to my wife yesterday, she actually didn't understand the one in the upper right. And my wife is ridiculously intelligent. She always keeps me on my toes. I hope you guys get these, right?
Yeah.
Seriously?
The whole 9 yards.
The whole 9 yards.
Oh,
Well, the first one I thought of is let's throw the kitchen sink at it, right? But so then there's the whole 9 yards, the whole enchilada, and the whole ball of wax. That's what's so. I didn't really find a good picture of the whole kit and caboodle. I mean, what the hell is it? What does a kit and caboodle look like? Right. But anyway, all right. So let's do all of that. Let's just see what this looks like. So we'll start with balanced differential interfaces, and this could apply. I'm kind of implying a digital interface here, but it doesn't really matter. It could be a digital or an analog interface. But let's start with balanced differential interfaces, and so you have a dedicated return current path. This up here if I can. There we go. I don't know if anybody online can see this annoying Teams window up here. It keeps getting in the way of what I'm trying to show. Anyway, so you have a balanced differential interfaces, dedicated current return path. And so this, I mean, of course, I've shown this in previous sessions, but I'm thinking in terms of a digital interface here. But again, it still applies if it's an analog interface. But thinking in terms of say like SpaceWire LVDS or RS422, what have you, you'll have your signal transitions ideally will perfectly line up. So you'll have high to low transitions on your positive side lining up with low to high transitions on your negative side and vice versa. So when everything is perfectly lining up, well, you have your balanced differential interfaces, you've got twisted pair of wires. Well, then your common mode current should be zero. The currents are always balanced and all is well. And we all live happily ever after. And do you believe me if I tell you that's the end of the story? So no, more than likely there's going to be some skew between these edges. And this is just one factor of many, just to illustrate the point. But if these edges are not perfectly lining up, which they may well not be, well, then at each one of these transitions, you're going to get a little blip here. You're going to get some blip of common mode current. And it's always at the transitions that this stuff bites you, right? When it's a nice steady state signal, all is well. It's the DVDTs and the DIDTs that get you. So you have these little blips of common mode current. That's what's going to generate your radiated fields. So we're talking about just a twisted pair here. So what do we do to counteract that? Put a shield on it, right? So now you have a shielded twisted pair. So that provides a path for that net common mode current. It'll minimize how much energy is available to radiate. You're now providing a path for that current, that energy to get back to the source. Okay, so it's coupling to the shield instead of just radiating out into space. So if it's a bidirectional interface, even if it's not, right, you're going to have noise sources in your receive circuit, right? I just do this to illustrate the point, but even if this is just a single directional interface, you will have noise sources in box B. You want to terminate that shield on both sides to provide a path for those noise currents to get back to their respective sources in both directions. Then you route that cable over a ground plane. Now you're providing a path for any energy that's not completely getting back to the source on the shield. You're providing an additional path for that energy to couple to the ground plane or the structure to get back to the source. And again, it's the method of images. However it helps you think about it, right? The method of images, I find to be a useful theoretical construct, but if you want to think more in terms of physical parameters, which most of the time I find that to be more useful, it's the capacitive coupling between the cable and the ground plane. Right, you're providing a capacitive coupling path with those high frequency noise currents to get onto the structure or ground plane and get back to the source. Right, and then an additional benefit of that's all in terms of emissions, but routing the cables directly over the ground plane also minimizes the loop area between the shield and the ground plane. So it minimizes that area for any magnetic coupling. So it helps with susceptibility as well. And now, if you have, it's very common on spacecraft where you're routing cables through bulkhead feed-throughs. It may not even be on a spacecraft. It could be, thermal vac. It could be, the MI test chamber, any kind of test configuration or what have you. You may be routing these cables through bulkhead feed-throughs. And if that is the case, if these are indeed bulkhead feed-throughs that are mounted to structure, you want to terminate those shields at every opportunity. So it keeps those common mode currents localized and it minimizes loop areas. And one thing I wish I put in the charts here, but Mike had brought up an antenna effect, right? If the cable is open circuited on either side, if the shield is open circuited on either side, it can behave as an antenna. Any of these cables can and will behave as antennas. It's just a matter of degree. And terminating these shields at each bulkhead feed through, both sides at each bulkhead feed through, minimizes the length of any individual shield. If you think of a shield as having the potential to behave as a radiating element, as an antenna, every single place you terminate it minimizes that available resonant length. Right. So if you look at this configuration, and let's just say each one of those lengths is a meter. So you have a full 3 meters, and you choose to isolate those shields at each bulkhead feed through. Well, you've got a 3-meter resonant length. And so that's going to that is likely to generate radiated emissions when that 3-meter length is most likely a half wavelength. I'm not going to go through the calculation at this point, but if you terminate those shields at each of those bulkhead feed-throughs, now your resonant length is 1 meter, and it pushes the resonant frequency up more. And at higher frequencies, it gets harder and harder to generate radiated emissions by accident. Not impossible, but it just as you make things shorter and push those resonant frequencies up, it generally helps. But it's just the point is that when you terminate those shields at each bulkhead feed through, you're keeping those common mode currents localized, and you're just minimizing their opportunity to generate emissions. Because that's another thing I see all the time is sometimes people think that they need to isolate these shields as they go through each feed through, and that's not what you want to do. I think this is all. Yeah, if you isolate it to avoid a ground loop, you're missing the point. You're missing an opportunity to shunt noise currents away from signal carrying conductors, which is the point of the shield. All right, so in general, a cable shield should not be used as a signal return. But what commonly used configuration do you think throws a curveball in that general statement?
Single-ended.
Well, not quite. Let there be coax. So the shield is the return conductor of a transmission line. So I'm not going to spend a whole lot of time on this, but at least it's worth at least mentioning something. So it's most effective at higher frequencies. We might still use coax at a kilohertz, but it's not really giving you your bang for the buck at a kilohertz. It's when you're at like 100 megahertz and above, when coax is really doing its best work for you, because it makes use of the skin effect at those higher frequencies so that the intentional transmission line signal current returns on the inner surface of the shield, theoretically. And then RF noise currents ride on the outer surface. So when you're at high enough currents and you're dealing with the skin effect, and so those noise currents are just on the outermost layer of the shield, then they're not really affecting your transmission line's performance. And so that shield must be terminated at both ends, primarily for your transmission line to work properly, right? If you open circuit the shield out of some desire to eliminate a ground loop or something, well, your transmission line is not going to operate correctly. Right, so you're totally defeating the whole purpose of using a coaxial cable for that interface. So, and it's also not going to shunt your noise currents away from the sensitive circuitry, right? So if you're using coax, you must terminate that shield at both ends. I can't even say you're missing the point if you leave that shield. Like you're not even in the ballpark of the point. You're not even in the parking lot. I think you're trying to attend a ball game in the wrong city. You're like in Cleveland wondering where Nationals Park is. All right, so terminate the shield of your coax. That's a thou shalt. And then the big benefit really for coax is that the return current is concentric with the send current, right? I don't have a corresponding graphic here, but if you picture a twisted pair, right, the send and the return paths are there's no way to get them to be coincident, right? They're offset from each other, and the twisting action basically just minimizes that offset, right? You're continuously twisting the plane of your loop to minimize the net radiated field and the net coupled field. But with coax, at least theoretically, the send and the return current paths are precisely concentric, so that if you look at the send current being, in the blue conductor, of course, we're looking at a cross section here. So that if with the send current into the page, per the right-hand rule, the generated magnetic field, magnetic flux is going to be in the clockwise direction. And with the return current coming out of the page, that magnetic field will be in the counterclockwise direction to oppose it. So theoretically, ideally, there's full field cancellation. The net radiated magnetic field is zero. Now, of course, we know that there's no such thing as zero, but so whatever manufacturing imperfections, you'll get some net field, but it should be minimized. It will be minimized with a properly built cable, and that's one of the big benefits of coax is that at high frequencies, and I didn't put the additional charts in here, but if you remember from the grounding session, they're at sufficiently high frequencies, you have kind of this transformer action. It's this mutual inductance between the send and the return paths that basically it will act as a transformer and essentially pull that return current path back on that immediately adjacent path. It's going to pull that return current back on the shield. Even going back to this previous chart, even if you have these two boxes mounted to a common structure, certainly at low frequencies, that if that's mounted onto a ground plane, that preferred return current path is going to be along the ground plane. But as you go up in frequency, and I talked about this at length in the grounding session, but as you go up in frequency, that mutual inductance, that transformer action between the send and the return current, the send and return paths, or in this case, the center conductor and the shield, it's going to tend to pull that current back on the adjacent path, right? And that was one of the nuances I pointed out then when we say current will follow the path. Well, first we say current will follow the path of least resistance. That's wrong. Then we say it's going to follow the path of least inductance. That's not really correct either, because the mutual inductance of this path is very high. It's much higher than the inductance between either of these paths and the ground plane. But it's because it's the mutual inductance, which is making it behave as a transformer, it's going to tend to pull that current back on the shield because it's the most adjacent path. At high frequencies, that's going to be the most desirable path. So the terminology we use can sometimes be very misleading and downright wrong, right? When you actually look at if you do an analysis, if you're a masochist like I am, maybe one or two other people in the universe who qualify for that, I don't know. But if you do the analysis and you're just calculating inductances, and you see, oh, there's this really high mutual inductance between them. So if it's mutual inductance, then it's going to tend to pull that return current on that path. That's a little, you have to think about that differently from just the inductance from, between one, the self-inductance of a conductor and its own return and its own loop, right, formed by its own return path. So that was a point that I made in that grounding session, that even when you say current is going to follow the path of least inductance, that can be a very misleading thing to say. So, but anyway, for coax to work properly, the shield needs to be terminated. Okay? But it can at least it has the best capacity for minimizing emissions, at least high enough frequencies where the coax is really working for you. All right. Doing okay for time here. We're actually getting pretty close to the end. So we talked about in the time and frequency domain session that you limit rise and fall times, that will limit your high frequency components. We have a simplistic trapezoidal pulse shape here. I mean, nothing really looks like this in nature, but it's a useful construct to simplify the analysis. That I went through the analysis of what does the frequency spectrum look like for a pulse of this shape as compared to, a rectangular pulse with essentially zero rise and fall times. For zero rise and fall times, you get this one corner frequency, and then the harmonics roll off at 20 dB per decade, which is the same as just 1 over F. But with factoring in the rise and fall times with this simplified trapezoidal shape, you get a second corner frequency corresponding to the rise and fall times, where you get an additional roll off. So the net roll off is 1 over F squared, or 40 dB per decade. So the basic message there is limit your rise and fall times, and then you'll limit this high frequency content, right? Well, so one way you do that is with filtering. So, and a big example of switching power converters are among our noisiest culprits. And filtering provides a low impedance path for those switching currents to return to the source. I mean, the whole nature of what a switching power converter is doing is that it's taking a DC input, our traditional 28 volts, where I think basically 30 or 31 is the new 28. Right? For several years, I think 30 to 31 volts is more standard, but we still will say 28 volts. But you get, somewhere around 30 volts, DC level coming in. Well, you're taking it through a transformer. Transformers don't like DC, so you chop it to form an AC signal. Some clock with a switching FET here that generates an AC signal going through a transformer, and then generally use pulse width modulation and a feedback loop to get the desired DC potential out here. But you're taking an AC signal that you've created from this DC input, and now you want to convert it back into a DC signal. Well, you need filtering to minimize that ripple, right? The very nature of this process generates a lot of ripple and generates a lot of noise, particularly common mode currents at these transitions. So filtering is all about providing a low impedance path for switching currents to get back to their source, and it keeps the currents localized to minimize emissions. And I do want to say, I don't know if any of our power brethren at Goddard are on the session here, but they're my neighbors over in Building 20. And these guys have really done a tremendous job over the last several years, the last several missions, several in-house missions where they have been the designers of this very circuitry. And I can't actually even remember the last time we had a significant problem with in-house DC to DC converter designs. They've just really done a tremendous job of addressing this very problem so that it's something that we don't even really have to think about. We can focus our attention on new interesting problems. But they have really, they just have a really good process, just design techniques for doing this filtering, so that we just don't have conducted emissions problems from these. It used to be like you could count on having waivers from, okay, we failed conducted emissions again. So this is just an example filter from an RSD design. I think it's just their LVPC, I think it's a general LVPC card that's used in a whole lot of different boxes. But you can see so you have your 12 volts coming in. There's some, I can get my cursor back. Yeah, your 28 volts coming in, and these are, a lot of these just use off-the-shelf converters, right? Sometimes they do homegrown designs, but this is just an off-the-shelf converter, and it's giving plus or minus 12 volts out. So it's a symmetric design here. You have your return in the middle. So you've got some differential mode capacitors, shown here, and stuff that's going to case. Those are your common mode capacitors. And then the chassis ultimately goes back to the return of the converter, right? But and now you have a common mode choke here that works against this impedance here. You have some additional filter capacitors. So is it common mode? Is it differential mode filtering? I think it's doing a bit of both. So but the real point here is that it's providing a localized path for those high frequency noise currents to return to the source. So here again, when you get back to that nonsense about current not flowing through a capacitor, I don't think any of us really believe that anymore. I just wish they wouldn't teach it that way so that we have to unlearn it. But you're making use of the fact that, high frequency currents do indeed flow through capacitors. That's exactly what you want. The capacitors are providing a low impedance path for those high frequency currents to get back to the source and away from anything downstream. Right. So, and that minimizes emissions, which is exactly what you want. And it allows the low frequency currents to flow out to the loads, which is what you want. Right. That's what a filter is doing, or, a low pass filter. It's passing the low frequencies, and the physical thing that it is doing to not pass the high frequencies is that it is providing this low impedance path. These capacitors are providing a low impedance path for those currents, the high frequency currents, to get back to the source and not out this way where they can generate radiator emissions or couple to other circuitry and generally wreak havoc. So filter connectors, I'm going to say are commonly used. I don't know how common. They're talked about a lot. I hear a lot of people say that they might use them and then end up not, but they're at least an option. Basically, they're providing capacitance from the conductors to the shell. They're by and large, I think all the ones that I've heard about are basically providing common mode filtering. They're just providing some capacitance between each conductor and the shell. I think you can get custom ones. You can probably get them with some capacitance between specific pins for a differential interface, what have you. There are different vendors. I'm not really going to go into that, but
So are you saying that center one there, I can't count pins on the left one, but that center one has 9 capacitors going from each of the 9 signals to the shell?
that's my guess, yeah. Or that I think it may just be like a composite capacitance. I'm not actually sure how they physically implement it, but I think the default, what I would imagine being the easiest thing to implement is just it's capacitance from each pin to the shell.
Oh.
But I know that there are different vendors who make customized versions of this, and you can probably specify, whatever it is you want, and obviously the more customized, the more expensive it's going to be. But I think the default ones that just provide capacitance to to the shell, I think are pretty readily available.
Yeah,
But
so John Carlisle makes custom filters, and you can put pi filter in there, so you can tell them the roll off you want, and they will tailor it to what you want. So basically, the pin goes through a ferrite, each of the pins, and then there's capacitors tied up on either side of that to the shell.
Okay, you say that's Carlisle?
Yeah, Carlisle. I
Okay.
think they might have been bought out by someone else now, but those are the guys who used to make all the custom filters for us. We flew a bunch of those on X-Risen,
Okay.
and Jedi.
But again, yeah, the designer must make sure the desired frequencies pass, right? These things are not all created equal, right? You don't, if you got a space wire interface running at 100 megahertz, you don't really want to be filtering that at 10 megahertz or what have you, right? So sometimes these are treated as a magic bullet, and I mean, just like anything else, I mean, you got to pay attention to what they're doing, and there are probably different options, and the more customized they are, I mean, that's great, but it does, that the more customized means you have more options, but it also means you got to do more homework to make sure that you're actually getting what you want. Because I think with something like this, it's really easy. I'm just conceiving it being really easy to having it backfire, right? If you didn't specify it correctly, you could have your circuit just not work properly. You might be filtering the shit out of your high frequency signals, but you're filtering so much that it doesn't work anymore, right? So. And nobody heard me say shit during this last session. So, all right. So just a brief word about magnetic shielding. Here was another place where I was struggling for a metaphor. Anybody get this one? A different kettle of fish. All right. You won't have to put up with this much longer. So, all right. So I'm not an expert by any stretch on magnetic shielding, but I thought it was worth saying at least a little bit. And I'll give a shout out to my friend and colleague Pablo Narvaez at JPL. This is a excerpt of a presentation he's given for the last several years at BMC Symposium on, well, it's on shielding techniques in general, with a big emphasis on magnetic. So magnetic shields redirect the magnetic flux so that it reduces the magnetic field inside the shield, and that's what you want. They do not reflect, destroy, or permanently absorb magnetic fields. And the whole idea is to provide a low reluctance path for magnetic fields to follow. It's really the same general principle as a current probe. I didn't put a picture here, but like if you think of this, the circular element here in the middle, think of that as a current probe, and you have a cable or wire going right into the page, right through the center of that. Well, the very nature of how magnetic current probe works is that current that you want to measure is not the thing you're measuring directly. You're measuring the magnetic flux that current is generating. So that current is going into the page. Lost my cursor again. There we go. If that current is going right in the middle of this circle here, going into the page, it's going to generate clockwise flux. So it's going to generate flux going in this direction. And so the magnetic core of the current probe is going to capture that flux, and then it's going to couple through the loop of wire, coil of wire that's wrapped around that core to produce a potential that's what you measure, right? So that's that magnetic core. I don't know, but obviously it depends on the current probe, but the permeabilities, relative permeabilities of those magnetic cores can be hundreds or thousands, right? You want it to be much higher than just air, right? Air having mu sub r of 1. So the relative permeability of the core of that current probe is going to be much higher than just air. So it's going to capture those flux lines, so you get maximum coupling into that coil of wire, so that you can actually measure the thing you're interested in, which is it's the flux generated by the current, which is ultimately what you want to determine. So it's the same general principle that magnetic shielding is going to use a similar type of material, some highly permeable material, with soft ferromagnetic material, right? So one material that we hear a lot is mu metal, and I don't remember offhand. This obviously was a bit of an afterthought, so I didn't do a lot of homework for this little bit here, but I don't know what the what the mu sub r mu metal is, but it's probably several thousand, maybe even tens of thousands or more. But whatever it is, like that's the idea, is that it's diverting these magnetic flux lines away from the stuff that you're trying to protect. Okay. So in that sense, it's a little bit, it's kind of analogous to RF shielding, where it's diverting the noise currents. It's not absorbing them, it's not making them go away, it's diverting them. So magnetic shielding is a bit different from RF shielding. It's got many nuances, and it can be rather invasive and expensive. Certainly if you're dealing with it like late in the game, where you've got some, and it's generally for low frequency. My general experience, my understanding is that it's for low frequency concerns. For higher frequency concerns, where it's generally more fully electromagnetic type of problem, the RF shielding techniques work fine, right? And I'll actually share I'll get through this. I'll share a quick little anecdotal experience I just remember. But it must be considered when control of the current return paths and loop areas are insufficient, right? My general experience is that you're best off for magnetic shielding to not be needed, right? If you control your current return paths and loop areas to the point where you don't need magnetic shielding, I think things are much simpler, and you're better off. But there come situations where, okay, it's not enough, and you do need to consider this. So I am not an expert, and that's as much as I'm going to say about this. So the recommended reference materials is the presentation that I got that graph and text from on the previous slide. This presentation from Pablo Narvaez at JPL, radiated electric and magnetic field emissions shielding mitigations. And I'll put that presentation up on the team site along with these slides when I post them
Yeah,
later today.
so John, one of the things we've used in the past is METGLAS, METGLAS, and there's
Okay.
different variations of that for shielding, magnetic shielding. You can get it in tape or sheets.
Okay.
And normally the victim is what you're trying to cover with that.
Okay. Yeah, I have heard of Matt Glass, and I guess that's generally mentioned along with mu metal. So I'll relate an experience from probably one of the early EMC symposia I attended probably 10 or 11 years ago. It was Dr. Tom Van Dorn at University of Missouri, I believe. I believe he's since retired, but he had been a pretty constant presence in the EMC community, and it was from a video set of videos that our branch got before I actually even took this job that actually was a bit of a turning point for me in terms of truly understanding EMI concerns. But I got to see him give some talks and some demonstrations at the EMC symposium a few years in a row. And he was giving a demonstration on shielding techniques, for electric and magnetic fields. And this demonstration, I just remembered where he had a coil. I'm gonna enable my screen here so you can at least sort of see how I'm waving my hands. All right, so can everyone see me? If you can, my apologies.
Yeah.
All right, this bloody thing is in the way. Like, if I click that, it shouldn't stop the recording, right? Okay. All right, so can you still see me? All right. Is anybody still there?
Yeah, we see.
Okay.
Yes.
All right, so you had this coil, right? He was just running a signal through this coil, and it was generating a magnetic flux, actually, pretty much like that RS-101 coil that I showed. It was just smaller. He had a coil of wire going around a magnetic element. It might have just been the flux generated by the coil of wire by itself, but whatever. But he was generating this localized magnetic field coming out of the coil. And then he had a receiving coil. So it was a kind of basically a qualitative, fairly crude qualitative demonstration, but what you do to get the point across. So you had a receiving coil hooked up to, I think, just an oscilloscope, right? So you could see the relationship between the received signal from the transmitted signal. And so you get a baseline, okay, with these coils, whatever, a couple inches apart. You're getting, say, 50% of the transmitted amplitude on the received coil. I'm just making that number up. But you get a baseline of what that is with nothing in between. Well, he started at low frequencies, maybe 100 hertz or less, I don't know. But he put a piece of, there we go, Missouri School of Science and Technology. It was University of Missouri Rolla. That's what I remember hearing first. But anyway, so you get a baseline of just what's the transfer function with nothing in between. And then he put just a piece of copper, just holding it with his hand. It wasn't even terminated to anything. It was just a hunk of copper. And at 30 hertz, 100 hertz, maybe even up to a kilohertz, there was no noticeable difference, right? It had no shielding effectiveness, which it won't at low frequencies. But then he cranked up the frequency, and I don't remember the specific numbers, but it's, again, it's the qualitative message. That's what stuck with me, that he got up to whatever frequency, megahertz, maybe tens of megahertz. Then you started seeing a significant attenuation of the signal. Right? You started getting a significant reduction of what the received coil was seeing. And that was with just with the hunk of copper, not terminated to anything. So for magnetic shielding at high frequencies, it was just about the eddy currents that were being set up in that hunk of copper that were sufficient to counteract the field that was trying to go through, so that the net field that reached the pickup coil was much less, and you got much less of a signal. So when he was doing this with electric field coupling, of course, the shielding element had to be terminated to something to provide a path for that current to go, right? As we talked about before. So for electric field and capacitive coupling, that thing you're using as a shield or as a barrier has to be terminated to something to provide a path for that current to go. But when it's magnetic shielding, it's just those localized eddy currents, at least in that specific example, were sufficient to counteract the field that was trying to go through and minimize how much was coupling into the receive circuit. So that was just a little anecdotal thing I just remembered, that it just illustrates how magnetic shielding is quite a bit different from electric field shielding. You have to think about it a bit differently. And it's not something that I have nearly as much experience with. So I'm just saying, just giving you a little bit of some what little I have learned. But if you're really going to explore magnetic shielding, that's something some people spend a lot of time studying and working with. Sounds like that was Richard, right? Richard Shimkevich.
That's right.
Yeah, Richard has sounds like he has a bit more experience about it than I do. So how's that for diverting signal energy? I'm going to divert your question energy to Richard. So Richard can field your magnetic questions once I'm gone.
I might
Don't
be
want you to
following
be-
you soon, John.
What's that?
I might be following you out the door soon.
Yeah, well, yeah, I think maybe I'll just leave that one alone. But yeah, I'm hearing that there may be a pretty good cue forming. But anyway, can you come back? Are you seeing the charts again? We're actually almost done here.
Yeah.
All right. And you got a quick view of Alfred there as we were in transition. So, okay, so this is what we just talked about. All right, summary. There we are. This is the last slide. So for conducted coupling, the best thing you can do is provide separate dedicated current return paths. Right? That's what you want to do to minimize conducted coupling. So again, certainly one of the first and probably least invasive things you can do is just separate your noisy circuits from your sensitive circuits. Right? That's not always obviously you may have physical limitations, right? If you're dealing with, say, a CubeSat or just something very small, there's only so far you can get with that. But that should at least be your starting point. When you know you've got some noisy stuff and you know you have some very sensitive things, don't put them right next to each other. So RF shielding will mitigate electric field and capacitive coupling, and it is actually effective with magnetic coupling at higher frequencies. But it's providing a path for noise currents to return to the source away from sensitive circuitry. It does not eliminate the noise currents, it is only redirecting them. It is only effective as the terminations. You need to consider the entire path back to the respective sources. And no pigtails, and we didn't hear the caveats from earlier.
I said no.
Ken can neither confirm nor deny that we had that conversation. So minimizing loop area and twisting center return conductors will minimize your magnetic and inductive coupling. Again, if twisting your conductors is not practical, like on a PC board, just minimizing the loop area is a significant improvement, right? You should at least do that, right? That's still something to do. That still gives you significant improvement, even if twisting is not an option. Routing conductors and cables over a ground plane provides an additional path for noise currents to return to sources. That's using the method of images, where the physical thing is that you're providing a capacitively coupling path for the ground plane to provide another return path for those currents to get back to the source. And then filtering returns the noise currents to the source to minimize emissions and reduce high frequency content. Magnetic shielding is addressed with high permeability material to redirect flux lines. And if you remember nothing else, in case I had forgotten to mention this, do you know where your currents are flowing? I've said it before, I'll say it again, that certainly when I was when I was an undergraduate, I guess I am about to retire. I'm sounding like an old fart, but there we are. But back in my day, when they all they really seemed to teach, or they emphasized potential. It was all voltage. That's all that counted. Your signal was all about voltage, and then current was just kind of this annoying byproduct. I mean, yes, of course they taught us that V equals IR and V equals IZ, but yeah, okay, if you're dropping a potential across some impedance, yeah, you're going to get some current. But we don't really worry about that. We just care about voltage, and that's something I hope has improved in the way they teach electronics over the last 30 years, because it's all about the current. You have to pay attention to where these currents are flowing, because that's where the problems are if you're not doing it properly. It's when these currents are getting in places where you don't want them to get, that's pretty much where all EMI problems happen. And it's all about the current. It's probably Mitch Davis, who was maybe one of my early mentors in this before I actually took EMI seriously as a career path. But I attended a couple of the courses. He had this job 2 people before me. And I think I first heard it from Mitch. Follow the current. Pay attention to where the current is flowing. And yeah, it sounds annoying. But I made this annoying by design, because I want to hit you over the head with this. If I think most of the people on this line already know this, but if you're new to EMI, this really is where everything comes back to this. I mean, I heard this for years, like, yeah, follow the current. And then after really being drawn in and dealing with a number of EMI problems, even before I guess I took this chief EMC engineer job, it's like, oh yeah, okay. They were all right. That's exactly right. It's all about where's the current flowing. So that's what you got to pay attention to. So that is what I have. Does anybody have any questions, comments? Discussion points?
I have 2 questions. I'll let people online go first if they have any.
Do any of yours have to do with pigtails?
Neither do.
Okay.
Although one of them,
Well, go ahead.
because Nick started to mention it. I have heard in terms of terminations of shields of twisted pairs, you terminate both ends on a digital harness, but you only terminate the source end of an analog harness. That is terminate the shield only at the source end. Is this a rule of thumb that should be followed?
That was what was in the SpaceWire standard for a while. That may be where that's coming from. They specified the outer shield was terminated to shell at both ends. So at least that was standard practice, and that's the way you should do it. The inner shields were terminated only at the source end, and then left open at the receive end. And then the SpaceWire standard was revised in the last 5 years, maybe, because I think it was in the early days of RST, because we were looking at this when we were implementing SpaceWire and RST. The SpaceWire standard was updated to at least provide an option. I don't recall if they still listed that configuration as an option, or if they simply updated it to say, no, we're going to just terminate the inner shields at chassis on both ends. I think that's my preference. I mean, I think just for all the reasons that I said here, I think a shield needs to be terminated on both ends to be fully effective. And I think they were able to get away with it because, I mean, they're using those micro D 9-pin micro D connectors. the conductors, you know, and the shield and everything, shield is a conductor. They're all in pretty close proximity so that even if you're leaving one end open, there's enough capacitive coupling in there for any of those high frequency currents to still find a path to where they need to go. I think they were kind of able to get away with it, at least is my general theory. But I've never really seen a case where leaving if it's truly a shield as opposed to, you know, as opposed to anything that's used as an intentional current return path, right? The shield should not be an intentional current return path, with the little exception of coax that we talked about. But if it's a proper shield over a bundle of twisted pairs, the shield should not be anything of your intentional return current path. And it should be tied securely to chassis at both ends. That's my take.
Okay.
You had a second question?
I don't know if you covered it in your grounding section. We love star grounds, single point grounds in our designs.
Mhm.
So that would generally mean that your power supplies should return through a dedicated path back to their source, to
Yep.
the ground point. However, I have been told that digital supplies, their returns should be tied immediately to chassis and go back that way. I've had it insisted upon me
Tied to chassis where?
at the source, at the local converter.
Oh,
Rather
talking
than
about the output. So like
the output side, yeah.
I guess I have seen that done. I mean, that's actually part of what I didn't really fully show I didn't show the full discussion that I think Mitch put in his slides. I put his name on the slide. I don't think I said it out loud, but then when I was talking about switching power converters, I said courtesy of Mitch Davis. He had stuff ready to go that I didn't have to redraw. But, and in talking with the power folks in building 20, I mean, I think they will, at least it's maybe I'm thinking of their filter capacitors. They'll for common mode filtering, they'll put their capacitors to chassis right there next to the converter. I mean, the one of the other factors is, you know, these power converters generate a lot of heat. You know, they just get warm, so they put them on a heat sink, generally speaking. And so that heat sink is the chassis of the box. So you can't get around the fact that the case of the converter is tied to chassis for thermal reasons, but it's also giving you an electrical connection. So at least putting filter capacitors to chassis right there at the converter, that provides like the most localized path for high frequency switching currents right back to the converter. But I think right there that is providing a connection of the signal reference of the converter is probably tied to its own case. So if the case of the converter is tied to chassis, I mean, that's giving you a chassis connection right there. I think for if you're talking about like, you know, a digital supply that's that probably has a lot of switching noise on it. You know, any path to chassis and then back to the source of that switching noise, the converter itself, is, you know, that's the most efficient path you can get. That's answering your question.
I'll reach out to you later today with a specific example I can show you.
Okay.
Although it sounds like you've done, I did what you are suggesting.
Okay. But sure, if we want to get a little further into the weeds, we can do that.
Yeah, I don't want to weed people across America.
I'm here. I'm here all week and next week, and then I will be going across America.
But
Anyway,
you don't want to tie a digital ground at multiple points in a box to chassis ground. That becomes a problem for the feedback circuit to the power supply.
Well, again, it depends, right? One thing I've learned is the answer to any of my question is it depends. But
Yeah.
I mean, like digital ground, if you're talking about like very high speed circuits, which they seem to be getting higher and higher speed, right? You got very high speed switching noise going on. I think a lot of people just treat their digital boards like an RF circuit. And with RF, you want to connect the chassis at every opportunity, right? By and large. Yeah. So Dependra is here in the room. He's in the RF group.
Yeah.
So he's done a lot of RF design, and with RF, the chassis is your friend. I mean, you want to tie the chassis as much as you can. Or, one of the things that, I mean, I've sort of hinted at this before as you go up in frequency and you hit resonant lengths, right? Let's look at some specific numbers here. If you've got a cable, let's just throw some ridiculous numbers here. If the cable is 30 meters long, right? The wavelength is 300 divided by, or I'm sorry, the frequency where it will be a half wavelength. Let me revise the numbers here. If we want our wavelength to be 30 meters, so if we say that the cable is 7.5 meters long, so it'll reach its quarter wavelength resonance. So when the wavelength is 30 meters, then it's going to reach it'll hit its quarter wavelength resonance at 10 megahertz. Right? Did I do that right? 300 divided by 10 megahertz is 30. That's your wavelength, 30 megahertz. So a quarter of that is 7.5 meters. That's not too unreasonable. I mean, 7.5 meter cables on spacecraft, we're going to be in that ballpark. So, and 10 megahertz is not a particularly high frequency. So that thing is going to be an efficient radiating antenna and a pickup antenna at 10 megahertz. Right. So one of the things I didn't really include here, but if you terminate that cable shield at as many places, I guess I did talk about it when you're going through bulkhead feed-throughs. If you terminate that cable shield like every meter, then that resonant length is now a meter and not 7.5 meters. And when you terminate the cable on both sides, then you're more likely dealing with the mode is probably gonna be a half wavelength resonance as opposed to a quarter wavelength. And you leave one end open, then you just sort of picture that end flapping in the breeze. The dominant mode is gonna be quarter wavelength. But if it's terminated at both ends, the mode's more likely to be a half wavelength. So at 1 meter half wavelength, the resonant length, it's going to be a 2 meter resonant length. So 300 divided by that's about 150 megahertz. So it's going to push the resonant frequency up to 150 megahertz. So it'll still likely resonate and generate emissions up at that frequency. But the higher up you push the resonant frequency, I think I'm just speaking off the cuff here, but I think the emissions will tend to go down. It'll radiate less efficiently the further up you push the resonant frequency. So
I think you answered my question when you referred to the RF frequencies with, I forgot your name. Deepan. In a star ground configuration, which is the holy grail of spacecraft design, which is to have a single tie point to chassis. What we do is, instead of running the returns of the secondary grounds on wires or conductors back to this single star point to chassis, we immediately bring those secondary returns directly down to chassis.
well,
And I think I'm hearing it's to get rid of RF effects.
well, the single point ground, like a single point ground, I don't believe in it as a holy grail, by the way, but a single point ground configuration for power it only makes sense when you're talking about like low frequency, like DC power or even like facility power. 60 hertz is effectively DC from an RF standpoint. Like the wavelength is about the width of the United States or something, half the width, whatever, it's thousands of miles. So when you're talking about low frequency AC power or DC power, then single point ground and you know, eliminating ground loops and all that makes a lot of sense, right? That's what you want to do to ensure that your DC currents are returning to that one point. And that they're not finding other paths. So those low frequency currents really are going to be exclusively mostly about true conductive paths, right? Capacitive coupling is just not going to be terribly efficient at 60 hertz, non-existent. But and certainly for DC power, that's what it is, right? It's providing dedicated paths back to that single point, and you're controlling the flow of all that, at least, so that's at least controlling like your DC magnetics and stuff like that. But when you get up to higher frequencies, maintaining a single point ground is I think is a lost cause, because you're going to have capacitive coupling everywhere, that those currents are going to flow in other places, whether you like it or not.
Yeah. Well,
And so when you just provide a path to chassis, like just a hard connection to chassis, I mean, you know it's going to happen anyway. If you try to lift a box from chassis, it's going to develop an RF potential with respect to the structure, and then that's going to radiate. And the best thing you can do is just tie the box to structure. But the part of your question there is you know, you're going through power converters in each box and going with like our standard approach of you're distributing your 28 volt DC to each load, to each box, right? And then the box is responsible for doing whatever it needs with that. So if it needs plus or minus 15, plus 5, plus 3.3, whatever, then, you know, thou shalt do that thyself. We're giving you 28 volts, right? So you gotta, you know, step that down and do all the stuff inside the box that you need to with that. Keep, from a DC standpoint, keep the 28 volt in return isolated from chassis. There's probably still going to be some filter capacitors in there, but from a DC standpoint, keep those isolated from chassis, so the DC current return path is going all the way back to single point ground. But then we generally take those power converters and tie the secondaries to chassis. And that doesn't violate single point ground, because those power converters are now isolated from the primary feeds. Like they have that transformer isolation from a DC standpoint anyway. And so the secondary, you know, the outputs of those converters, plus minus 15 volt, 5 volt converters, generally the best practice that I've seen is to tie those returns to chassis, like right at the converter. And especially, I mean, for higher frequencies, like for high speed digital logic, I think that's commonly what's done. You just tie everything to chassis. I mean, you have a ground plane, right? A 5 volt, showing my age there. Digital's still 5 volts, damn it.
Yeah.
Do we do anything with 5 volts anymore? Or is it all 3.3 and 1.5 and like 0.7 or something? I don't even know. Doesn't matter. But you know, you have your reference plane, and you know, if it's high speed digital logic, that reference plane, you know, is tied to chassis like all around the perimeter. Like there might be tie points to chassis, like not just at corners, but like every couple of inches or something. And I mean, I don't know if this is really fully answering your question.
No, you've disabused me of single point ground being a holy grail, but I wasn't expecting a kind of Spanish Inquisition.
We got to get on the bus and ride across town before the episode ends.
Yeah.
Don't throw Python references at me without facing the consequences.
Plus, we're old.
Exactly.
People don't know Python.
Yeah, must be true. Does anybody else have any questions? I can stay a bit past 11 o'clock. Hey, this is the last session I'm doing, so, you know, I can stay a little bit longer. I can stay after class. No questions?
Just a comment, thanks. It's been great.
Well, but before I go there and get gushy, I want to, since Ken threw out a Monty Python reference, don't worry, I'm not going to start like throwing back multiple Monty Python references, but I'll just say over the weekend I read where Eric Idle had commented about, I don't know if he's being interviewed or whatever. I just saw this excerpt, but, he says, I think it's wonderful that people still pay attention to what we did 50 years ago, that Monty Python is still entertaining people. But he says, I'm actually a little perturbed that we're remembered in kind of this, how did he put it? Kind of like cuddly, cuddly cutesy kind of way. It's like we weren't cuddly and cutesy. We were pissing a lot of people off and the BBC was getting angry letters about us every week. That's the way I want to be remembered. That was a lot more fun. So I think maybe I'm taking a cue from that. I don't want to be remembered in a cuddly cutesy way. So
Yeah, in many ways, the founding fathers were not cuddly and cute.
well, exactly. Yes. Yeah, it has been a very it's been a very, I wouldn't give the last 36 years for anything. It's been a great ride. Um, I'm definitely ready to plunge into this next chapter of my life, whatever that ends up looking like. Most immediately, it's going to be on my bicycle, exploring the country. I made it to Pittsburgh a few weeks ago, and I'm gonna get back there. My daughter's gonna take me back there probably on my last day, next Friday, and then I'm gonna hop on the bike and keep going. And got some people to visit along the way, and things that I haven't seen, some bucket list items that I want to see along the way. And as I think as you may have perceived, this EMI is, I mean, this is true, I think, for just about everybody I've met in the EMI community. It's way more than a job. It gets into your soul, into your gray matter, and I mean it has to, right? Because we spend so much of our time convincing people that our discipline even exists. So for anybody to really pursue EMI as a career, if you last any length of time in it means you've got a passion for it. And I didn't expect it, because I hated this shit when I was an undergraduate because it wasn't taught very well. So I'm certainly glad that I had an opportunity to say, okay, here are the ways I don't want to teach it. I just sort of reversed the polarity on a lot of the ways I learned this stuff and said, okay, let me try to do it a little differently. But you know, but the whole point of that is while I might disappear for a chunk of the summer and ride my bicycle, I'm really not intending to go away forever and ever. I will most likely be back in some capacity in around the fall time frame. And whatever that ends up looking like, I don't know what kinds of uh, I was going to say what kind of interesting work is going to be happening here. I'm not beyond naming names. Brad Kercheval in the Power Group is my next door neighbor at Building 20, and Brad, I think I've discovered somebody who has a darker sense of humor than mine, and that's been interesting to see. But anyway, a week or two ago, we were talking about this very thing, and I said, I don't know what kind of interesting work there's going to be to do here in September, October. And Brad says, "You just mean work, right?" Yeah. So yeah. So I will definitely be in touch, and I will see what kinds of support I can still provide. And I'm been handing out cards. Ken, I think you're the only one who doesn't have one. I'll give you one when we're done here. But I think I've sent out contact information just on the email list. So and I have made a farewell video. I actually put the finishing touches on it last night. And I want to share it with some people here, here at Goddard first. But once I'm ready, I'll provide the link out so that you can watch it at your leisure. It's about 21 minutes. I figure summarizing my 36-year career in 21 minutes is not too bad. But yeah, it's been a great ride. I really it's been an amazing honor to work with the best of the best, because I had to bring my A game uh, to keep up with all you guys every day, and that's you can't put a price tag on that. When you're working with people who really make you bring your best game to the table every day. So that's as much gushing as I can do right now. But thank you all for a great ride. Thank you for participating in these sessions. I'm certainly glad to do it. I'm glad that they're helping people make sense out of this topic that I wish wasn't made out to be as hard. People make it out to be a lot harder than it is. And in fact, that's one of the principles I've left on the screen there. Like there are some fundamental things to just pay attention to, and you realize everything kind of comes back to, where your current's flowing and just some basic principles. There's things that you can just pay attention to help make sense out of it. I mean, it's all physics, which when I cracked the inner logic, well, I'm consistently continuing to try to crack the inner logic of EMI, right? One of the cool things is that there's always some new stuff to learn about it. Every troubleshooting effort I've gotten pulled into, it's like, well, I haven't quite seen that before.
How did they do that?
Right. But at the heart of it, once you actually get to the heart of the root cause of any given problem, it's, well, of course, that's what physics is going to do to you when you do that. It's all physics, right? You have no choice. That is what physics will do when you configure your system that way. Which I think to me, it's very satisfying when you get back down to the laws of physics. Like you don't really have any choice. That is what's going to happen when you set things up that way, as opposed to, like, say, microprocessors or something where you're having to get inside the sick mind of the designer who came up with that instruction set or what have you. I'm actually quoting somebody, a colleague. You remember Dave Bergman?
Yeah.
Dave left Goddard probably 25, almost pushing 30. But I regret losing touch with Dave, because I think we never hung out outside the workplace, but we'd go to lunch or whatever. I think we got to be pretty good working friends, and we would just kind of compare notes on things, and we learned from each other. And I remember him saying he was I think one of the first analog designers I really interacted with. Before kind of what helped me go into more analog design. Once I got into that, this is a whole lot more interesting. And he said, what he likes about analog design is if that op amp is oscillating, it's not the op amp's fault, it's your fault. You don't understand where, whatever the stabilizing capacitor needs to go, which probably says in the data sheet. But if the op amp is oscillating or doing something weird, it's nature. It's not the op amp's fault, it's your fault. But he's the one who mentioned, like, the sick instruction set of a microprocessor. Like, with a digital problem, there's a whole lot of things that you have no control over, and you're trying to reverse engineer what some other person thought was a good idea. And I've applied that to EMI as well. By and large, I mean, you still are having to deal with some sick decisions somebody made. But again, it's all the laws of physics. Like, what is physics going to do to you once you've made that decision to set up your system in a given way? So anyway, hope that's not too much gushiness for everyone. That's my version of cutesy and cuddly.
Initiation.
It's way too much cutesy and cuddly and gushy for Ken. All right, anybody else have any parting thoughts? Did I alienate everyone? Is anybody still out there?
No, it's been great. Thanks.
Yep. Well, I can say, well, I'll be in touch. I'll send the link out to my video, but once I've had a chance to share it with some people first.
And for
Hey,
you
John,
old
this is
folks out
Richard.
there, I
What's
put in the
that?
Clean
So-
Bicycle song link.
What's that?
So, John, while you're cycling across the country and something comes to you about EMI, maybe you need to post it somewhere. You're going to have a lot of time to think as you're cycling on that bike, avoiding
I-
trucks.
Well, I'll be putting stuff up on Facebook, and I'll send out. Actually, I was gonna say I for my trial run getting to Pittsburgh, I was putting stuff on Facebook and sending out email updates. So if you want to get on my email list, just shoot me an email, and I'll add you to my list. I'm doing it on my phone, of course, for my personal account. So, but yeah, I'm happy to add anybody to the email updates. And just once I have the list, then it's just sending to that list every time I want to send out an update. But I don't plan to be thinking a whole lot about EMI while I'm on the bicycle, but you never know. You know, that's honestly, I like benefit of like cycling to work. I have had some like have had some neurons make a connection when, you know, that's kind of what happens, right? Sometimes you're beating your head against a wall on a problem, and it's not until you just step away from it and let your brain relax a little bit, and like you're on a bicycle or doing something else that you find relaxing, like, oh, hey, that's the answer. Or that's what we ought to try. Whatever. So it might happen. I'm not gonna make any deliberate efforts toward it. Let's just put it that way. This whole bike trip, well, you might say it's more about soul cleansing. It's honestly something I just feel like I have to do. I've been musing about it for a while, for I don't know, about decades. I've only really been into bicycling since my mid-30s, but I've gotten the bug, and the week to Pittsburgh was, you know, went really well. I'm like, okay, I think I can do this. So if people are still interested in this, and we're definitely done. So if you want to bail, that's fine. But a quick anecdote on that trip to Pittsburgh. Um, I did bring camping gear. I camped a couple of nights, but I did stay in hotels the first 2 nights. And I got to Leesburg. It's about 50 miles from my house, you know, the first day. And I was leaving I was leaving afternoon. So I was like, I don't want to get to Leesburg at some hour and then have to set up a tent. Forget it. I'm going to just stay in a hotel. And there were some other bicyclists at the hotel. When I was going to get breakfast the next morning, you know, I was just getting up. I was nowhere near ready. But I saw these two guys in the stairwell. They had locked their bikes up in the stairwell, and they were getting ready to head out. And I struck up a conversation with them. Said, yeah, and they were clearly, you know, on a self-supported tour. They were loading stuff up on the bike, and struck up a conversation, saying, "Yeah, I'm about an hour behind you." And they were going in the opposite direction. They were going toward DC, and I was going away from it. But I noticed that they had about a third of the shit that I was carrying with me. And I'm like, how do you do that? How are you like, because they said it, they had already been on the road several days. I think they were ending up in DC. So they'd been on the road for a chunk of a week. I was like, how are you doing it without all the crap I'm carrying with me? I had, you know, front and rear panniers, 4 full panniers, plus a bag of my tent and other camping gear strapped to my rack. You know, they're just like, well, for one thing, how many changes of clothes did you bring? I said 3. You know, I knew it was going to take me 3 days to get to my friend's house in West Virginia. So I never had to recycle. I got 3 days to Romney, West Virginia, did laundry, 3 days to Pittsburgh, did laundry there. 3 just seemed like a good number. And bike clothes are fairly light. And then I had two sets of clothes to wear in the evenings, a couple of t-shirts and, you know, pants and whatever. And they said, oh, well, there you go. We didn't bother with any spares. We're just wearing these same clothes every day and we smell bad. And I just took that and I said, you know, thank you for the suggestion, but I think I'm going to keep doing it my way. Like, I don't really want my
Yeah.
bike clothes to become sentient and then stage a rebellion. Do you have a comment, Mike?
No, just that's, yeah.
It's like,
Right. Nice
I
and
mean-
ripe when you get to a friend's house.
yeah, that's just, that's one place I don't think streamlining is, that's not what I'm gonna do there. You know, there are a couple of other places where like, okay, I took a spare of this or a spare of that. It's like, okay, I might be able to get by without that. Like one specific one, which, you know, like camping headlamps. I had two of those that are USB rechargeable, right? So I brought them both. I threw them both in the bag. And then I realized for this next leg, okay, my backup for camping headlight are my bike lights. I'm bringing a spare bike light, both front and rear lights. So like, okay, I have two lights for my bike. That will be my backup one headlamp or light for, you know, for camping if I need one. That's not much, but it's like things like that where if I, you know, that's where I can streamline, you know, without really compromising system performance. You know, but the single set of bike clothes, like just my brain, I couldn't even get my brain around that one. Like why would you even think that was a good idea? But I guess maybe that's a way of having the trail to yourself. You get a wide berth.
Keeping
All right,
tents
what-
separated. Okay.
That's right. Right, so separating, you know, that's definitely a way of separating your culprit from your victim. And the coupling mechanism is very strong there.
Yeah.
Okay, with that, I think that's a pretty good indication we're done here. But thank you all. I'll get this stuff posted here later today or tomorrow at the latest. Today's shaping up to be kind of busy, but anyway, I'll get this stuff posted and thank you all and may see you again sometime soon.
Enjoy. Bye.
Here's
Happy trails.
Down, go all the way to the right where the down carrot is.
Yeah.
This one?
Keep going. Keep
Look at
going.
the big red one right there.
And,
Yeah.
and you,
Well, I quit out of the meeting. I'm trying to stop the recording.
Well, when you're in the meeting and write everything.
yeah, meeting is so different. They're full there.